Good morning, everyone. Yeah, that's better. Listen, I came across with the work that Manu Prakash does because I was writing a paper about a history of one computer that works with water, that models a economic system, right? That computer is called Moniac. It was built in the UK by an inventor from New Zealand in 1949. And to conclude the paper, I was checking for new implementations related to computation and water. And I found a very interesting laboratory in Stanford University that was working in a computer based on water droplets. Yes, water droplets that have binary states with polarization and can perform computations. And I was mind blown by this idea. Then I discovered that it was the lab by Manu Prakash. But that was just the beginning. I was mesmerized when I found that he was also very engaged in the impact of science, the impact of science, in society in general, but especially in those places that are in need for scientific tools, for instance. So the last year, SIGGRAPH 2024 gave us a gift announcing SIGGRAPH 2024, the Foldscope. That is one of the inventions of Professor Manu Prakash, who is a professor at Stanford University. He was a MacArthur Fellow and is the champion of the frugal science concept and practice. So as you can see, we have all our themes back again, right? From the macroscopic to the built environment, to the body, to the built environment, to the city, the world, the cosmos, yesterday morning, remember, and imagination, right? So we will go back to microscopic. And the interesting thing is that we are transitioning from yesterday's night, real-time live, and this is going to be like an announcement. And now it's going to be real-time science with Manu Prakash. Please help me welcome Manu.
Thank you.
Thanks a lot for coming.
Absolutely. Thanks for coming in the morning. I want to talk about imagination today, but I want to talk about failures of imagination. Failures because we built a society with haves and have-nots, and a tremendous amount of people suffer because sets of technologies that we have built, solutions we've built are absolutely inaccessible. I'll also talk about how to overcome these class of failures of imagination by literally looking in the microscopic world. So one of the things that I deeply care about is sharing the sets of tools, tools to empower and cross the sets of barriers. And often we frame this term in the context of magnifying curiosity. You're all born curious, and often enough, not just people in this room, but everybody around on the streets. What does it mean to remain curious in our lives? And are there sets of tools that can empower us to do something like that? And if there is one thing I want you to take away from this talk, is just this one saying. I teach a class called Frugal Science, and I had a student from Sudan, and I was having a conversation with him. This was literally 2 days before war broke out in Sudan. And he said, Manu, we have a saying in Sudan, which is, don't build a pen that doesn't eradicate ignorance and shame. Pen was the emblem of, it's quite an old saying in Sudan, pen is an emblem of technology. And it resonates with me quite a lot because often when I'm thinking about technical solutions, it is important to all of us of what they do in hands of people around the world. So let me share the first 5 minutes of just absolutely depressing news, primarily because I can't sleep at night and I want you to not sleep at night. I travel a lot. We work a lot in Africa. And this is a photograph that I took in Ghana a couple years ago. This is a hospital. This is also a bus stop, and roughly 1 billion people call this essentially the access to health care. There is maybe or may not be a nurse or a doctor in that van. Many of the kids here that you see in this photograph actually have malaria, a disease that, unless treated within 7 days, would lead to death. That's the reality of 500,000 kids on this planet that succumb to malaria every year. This is one of our field sites in Madagascar. We walk 12 to 14 hours on average to even think about arriving at any health facility, for example. This is the story of a large part of Africa, significant portions around the world itself. And to make matters worse, if you were to think about diseases and things that are far away, infectious diseases are on the rise. Malaria, which we have actually curbed down for the last 50 years, for the first time in history of malaria, the trajectory of number of cases are actually going up. This is another photograph that truly reminds me of why I lose sleep. This is a photograph in Uganda. You can see a couple of kids. And what haunts me in this picture is that these kids are playing on the graves of their brothers and sisters. And you usually bury your children right in the front yard because you don't want to forget. And we can't even get there, forget about trying to understand what we might be losing, and these oceans are changing. One of the factors of thinking about these sets of oceans, which if I get time in the end, I want to take you to the Pacific Ocean because I just got back 15 days ago, to just share with you just also the challenges of what does it mean to operate and work in many of these areas. Why should you care about this is the fact that unless we understand our oceans and the mechanisms it sequesters carbon, we would be in deep trouble because we have no idea what the tipping points of carbon sequestration in the ocean looks like. While 30 to 40% of all carbon that we emit every day is essentially being absorbed by these sets of mechanisms. We haven't built a system as yet in which we could truly say that science is for all people. I grew up in India, and one of the things I explicitly remember is I was given a high school exam to draw a microscope and label every one of its parts. Except I hadn't actually seen a microscope before. I had seen a photo of it in the book, and I was supposed to draw the same perspective that the author had drawn in that book. Until today, I recently picked up some of the exams from places around the world. That exam question still stands. For COVID, many of you know what happened to education. It's roughly 500 million kids had no access to education during that time. So one of the things that reminds me over and over again when I think about this is that just a roof doesn't make a school. It doesn't, unless you can give access to curiosity, it's incredibly difficult for the next generation to be tackling and thinking about these sets of problems that I'm talking about. Now, as technologists, you could all argue, is technology the answer to all of this? And what I'm here to tell you is, without the human element, without our efforts to make sure that this technology is in hands of people around the world, it's a lost cause. And the best way to think about this is actually healthcare itself. When you think about biology and the abundance of biology, that all of this technology, that biology, enzymes, molecular reactions, all self-replicate, and still we have such fragile health ecosystems. And the fact that it's been said very well that from a context of inequality, it's the greatest injustice if you were to think about in terms of lack of access. So that's the depressing part of the story. I'm talking about healthcare challenges, I'm talking about environmental challenges, I'm talking about educational challenges. They're all linked deeply together. And one of the things that I want you to think is take this from a perspective of every one of the challenge that I noticed and mentioned actually has a microscopic origin. Diseases, when you start thinking about what's happening on our planet from a microbial scale, and also what does it mean to really discover this microbial world. So I'm going to take you through a little bit of this microbial world and share at least a philosophy that we have used for the last decade in trying to tackle these challenges. I'm not saying that there is a silver lining in any of this, but I deeply care about every one of you at least thinking about these sets of challenges. So the microbial world is bizarre. I think that's the appropriate word that I can share with you. Every one of these doodles that you see right here is a living organism that hides. Some of you might have met them. They are some of the strangest creatures. Some of them are living in your brain right now. 1/3 of us have this. Microbes and eukaryotes that are neutral to your body but just love living in the brain. Some of them will eat your brain too. So, they're not all lovey-dovey. But some of them are just the most beautiful, wonderful life forms that shape this ecosystem. But most of us don't actually have access to be able to explore this microbial world because it's inaccessible to our naked eyes. And when I think about this as a grand challenge, I often think that what it requires, the microbial grand challenge, is access to tools that operate at a planetary scale. It requires a deeply inclusive environment where scientists and non-scientists can truly work together. And historically, there was one time when this was explored, and that has to do with an object on the screen. How many of you can recognize that object? So that shows the age of the group too. That's Sputnik, a basketball-sized object that scared the hell out of everybody, frankly. But ironically, when it was launched, there were people in the Smithsonian who were thinking about the fact that we did not have any tracking technologies to know where these satellites are in the sky. And a phenomenal person, Fred Whipple, thought about this challenge and built what is called the oldest citizen science program, which is at that point called Operation Moonwatch. And what he did is literally spread tens of thousands of telescopes, $10 telescopes, in hands of people anywhere in the world. 50 countries participated, and they were competing with literally $1 million automated satellite trackers that the defense was working on. And for the next 60 years, this is the community that tracked all of the Sputniks. This community is really why we have amateur astronomy, that the only supernova that has ever been seen exploding was actually seen by an amateur astronomer in Australia. And one of the beautiful things about this is that it inspires people to engage in the process of science rather than just observe it from a periphery. And I love this quote. There are thousands of examples. The James Webb Telescope designer was actually a member of Operation Moonwatch. And I love this sort of a quote around, this was a 17-year-old who had seen Sputnik, and in the very end of his story, he sort of writes that sadly my Moonwatch scope was stolen in 1963. So, I think when you think about this, that it's not as if we have not done and built community programs to change and face some of the largest challenges. Frankly, our global health program around community health is one of the largest citizen science programs in the world today. So many of you sit here, and many of us were safe from a crisis like Ebola. This is a photograph from Liberia, a friend of mine. She was out in the field at that time, going to villages tracking Ebola, some of the most dangerous diseases in the world, with a little backpack. And when you think about the sets of citizens, they have high school degrees. Some of them don't even have high school degrees. Many of them are on volunteer program, engaging in the sets of processes and challenges. And one thing that we've been thinking quite a lot about is what are the kind of tools that we can put in the hands of people like this around the world to really face this microbial challenge. Also to enable discovery, but at that same time, apprehend some of these sets of challenges. And I brought some of the tools, so I'm hoping that if I don't overrun in time, I'll do some demos so you all get a chance to see some of these tools. We've spent a lot of time out in the field talking to communities, sharing sets of ideas, learning from them, both in the context of health, but also in the context of the environment. I spend a significant amount of time at sea. This was one of our recent expeditions in the Arctic. And again, the same sets of challenges of robust tools that can operate in environmental conditions to really explore the microscopic world. We've done 17 expeditions so far, and the beauty of the challenge here is the fact that it's incredibly expensive to be at sea, and you have to be thinking about the same sets of design challenges that you would think about in the context of healthcare. So let's walk through a few sets of examples so this becomes a little more visceral and direct for you. The framework that I often use in most of this work is what I call frugal science. The idea that cost and performance have to be thought in together to be able to build and design solutions. And often enough, I'll give you a few sets of examples, starting with a very simple object that's called a foldscope. How many of you have used a foldscope here before? Okay, only a few of you. So at the end of this session, you can come out and see this object. Around a decade ago, I was starting to think about this problem and started realizing that without access, we will not be able to tackle these problems. And we put ourselves on a challenge. We said, could you image a single bacteria for a price point of less than $1? It took us many years of work to be able to do that. But at this point, Foldscope, which is an origami microscope, can image a 700 nanometer object at a price point of $1.75. And I'll just show you kind of a little bit of a history because there is a historic context to this. So I'll let you just watch this video for a second. All the pictures and data that you see are coming from this object that you put together and built. There's a little bit of an irony to this. All fun ideas start on a piece of paper. This one ended up remaining on paper.
That was really what part of our inspiration is to think about a microscope that could literally be $1 or less.
People found that silly, primarily because, of course, I said, oh, the right way to manufacture microscopes is out of paper. And that by itself was laughable. That was the grant that I wrote to the NSF. I was finally surprised that we were supported to pursue this idea of what I called print and fold optical instruments. So I think this is going to go on for a while. I'll just narrate and shorten the history. One of the challenges that I was thinking about at that time is access. And manufacturing was one of the key aspects to be able to do something like this. And long story short, we were able to both build and manufacture. We built, the first 100 instruments in the lab. We wanted to start sharing them with people around the world. And something surprising happened. We published a paper describing this work, and I was very happy, as all of us are when we publish a paper. And the next day, nothing in the world changed. The world was still the same. Everybody still had no access. And it dawned on us at that time that, to truly prove a point, we have to take it on our own shoulders to be able to build and design this and scale this. And ironically, around that same time, this appeared on Twitter, and it really irked me. This was a tweet by Bill Gates. He had somehow read our archive paper. So, this is in the preprint, and he wrote this thing, $1 origami microscope, ? Interesting. And what irked me was the question mark, was the fact that he was either questioning whether we could do this or not. But no jokes. What we decided to do is start a program where on our website we said this is just in a research lab at my lab at Stanford. Anybody in the world who wants a microscope, we will ship it to them. We had planned to make 10,000 instruments. We got 70,000 requests, and we shipped around 100,000 microscopes in a period of 6 months with the primary goal of just making access. We just cared about what would people do with these tools. And that led to the birth of Foldscope and the Foldscope program. At this point, 10 years in, it's the world's largest microscopy community. We have shipped more than 2.5 million instruments to kids around the world. And what I love about this is the fact that it's not about the tool itself. The tool is right here. Any of us can build it, play with it. It really is about the community. And one of the premise of this was we can build and manufacture tools, but we cannot manufacture mentors. What I love about these parents, this is my favorite Foldscope photograph, is they're not sharing the microscope with their own child. So be that parent. Engage in a process that is so deep and it percolates. That's really the process of science. Now, this is not just a toy. It actually is a high-power microscope. So this is phase contrast imaging of single cells, single bacteria, ciliates walking around, and you're starting to get a taste of what that infrastructure looks like. There is an entire software programs that we have built, an online community, AI-driven identification for these sets of microbes. And what that has led to is really a remarkable community of curious people exploring our world. Hundreds of species have been discovered with this set of a tool. These are used in diagnostics around the world. We have users all the way from 4-year-old to 90-year-olds exploring and sharing what they think. This is the community website. While I'm having this conversation, somebody somewhere around the world is exploring and sharing their observation on this community website. And one of the things that gives me great joy is the fact that many of the discoveries are not just made by us, they're actually made by community members that had never gotten a place in science. So what you just watched was Kaziranga. These are the guards that protect the rhinos in India. And when I ran that workshop, they kept their guns outside the room and came in and engaged in the process of science. This is a sandfly from Panama that carries leishmaniasis. And here's immune cells that you can watch in a body. This is a developing ant. All of this data comes from the community, from people that I've never met, I've never directly engaged, other than making these sets of tools accessible. And the ownership of the program has really belonged in the community, to an extent where we work programs in Iraq, Afghanistan, Sudan, places which are very difficult to work in, primarily because the community members taken upon themselves to engage and teach and train people around them. So this goes on and on and on, and this video is online. But one of the most beautiful aspects of this is what discoveries people actually make. There's a very large-scale program we ran in India, in rural India, to try to understand the role of engagement of communities in these sets of programs. And one of the things that's been really powerful is the advent of cell phones. You don't need a cell phone to use this tool, but if you have one, you can augment and collect sets of data sets. And a lot has been written about this, and most of the discoveries. We've just written one paper. 700 or so papers have been written by people in the community itself. So, one of the things that I want to share is, what do people do with these sets of tools? So this is a case in agriculture for plant pathogens. Here is a sailor that will show up again. This sailor literally does actually sail with his chicken. So it's not a prop. So animals for the first time observing the microscopic world. There are sets of communities all across the Amazon. And one of the things that's really heartwarming is the fact that the community explores in the languages that they deeply care about. So after English, Tamil is the most spoken language in our community. This is the community in Iraq. And Mohammed, who's been running this program for the last 140 days continuously, he's been traveling across Iraq, running these sets of workshops. And one of the things that dawns on me when I think about this is the fact that I would have never met these people sitting in my office thinking about the problems or thinking about trying to even tackle any of these sets of problems, let alone engage with anybody, unless we shared the tool. And it's been really powerful to be able to think about that sharing. And at that same time now, with the advent of cell phones and connectivity, we've been able to build learning experiences on top of this. Because this is a SIGGRAPH and the gaming community, I want to share a little clip of a microscopic game that we're working on that augments and builds, allow people to understand how to navigate the microscopic world. So this is a work in progress, but it's valuable for you to understand that both there are virtual experiences and real experiences that you can have while directly. So to unlock any of these microbial organisms, you have to first find it in the real world. So you can see I'm wearing a tardigrade t-shirt. If you're going to take that avatar, you don't just choose it. You go out there in your streets, search and find that organism. That's how you unlock many of these sets of, or you can share that. If you have an organism that you've captured before, there's a playing card. This is Pokemon, but for real. There are real monsters in these cards, and you can share and trade them back and forth. And you build a sense of the microbial world from ground up by actually exploring. So this was about the terrestrial world. I think I had mentioned something about the ocean. And one of the challenges when I told you that I spend a lot of time on boats is, I need to explicitly mention this, is I spend between $60,000 to $70,000 per day to be at sea. So for a 35 or a 40-day expedition, you can see I'm spending just a couple $1 million to be at sea. And this is why it's incredibly difficult to know what's out there. We've been thinking about this problem for a while until we met this person who is one of the youngest sailors to actually cross the Canadian Passage, and Gurek. And one of the things that fascinated me was there is literally 15,000 to 20,000 sailors right now in the ocean just exploring for recreational purposes. And we decided to build a program to enable their small sailboats to be research vessels. We built a genomics program and an imaging program, which now this tool is called Microscopic. It's the bigger brother of Foldscope, but what this allows us to now do is to do automated imaging of what's underway on your boat. So this is in a Lake Chilliwack. This is one of the UNESCO World Heritage Site. This is the older version of Microscope. And what you're watching is, I brought some samples with me. This happened to be from the Amazon River. I was in a place where illegal gold mining is done, and I was trying to figure out how much gold is there in the silt after all. So there are shreds of gold possibly in this little bucket. And what I'm going to do is to just share this. You load it right there. And if we can switch to the other computer for a second. Right there, I'm connected to this instruments. You're seeing live what I've just loaded in, and I'm going to turn this pump on. And what's flowing real time is clay, microbial matter, and the system is imaging every one of these organisms simultaneously as it goes along. And while I finish this talk, I'll actually continue running this. And the sets of a system can then essentially analyze every possible object that you see. So Foldscope allows us to do this manually. Now this is completely autonomous, driven by, and literally in this little vial of 10 ml, there might be 1 billion organisms. And many of them we might have never actually seen before. So if we can switch back to the slides, and I'm going to come back to this demo in a second. As you can see, this is built out of bamboo. Primarily from a context of thinking about changing people's mindset around instruments. When we invented this tool, it's completely open source, by the way. Every single instruction of how to put this together is online, and we essentially put that on a website. And over the years, the last 2 years or so, people have been building this set of a tool, archiving microbial diversity wherever they find them. So if you go to planktoscope.org, you can find the instructions of how to build it. We validated this tool for a price point of roughly around $600 in part. It competes with instruments that cost between $100,000 to $150,000. And that's really the power of frugal science. Once we have collected this data, then the action begins. You can analyze all of this in an autonomous manner. This is what I call an ecogram, just like Instagram. It's actually a photograph of the ecology. So any water point, any aquatic environment, one of your taps, for example, I hope that doesn't have all of this. And you can analyze this to ask yourself a question: how healthy is this ecosystem per se? And once we initiated and shared this, people started sharing these photographs from their basements, and it started to grow. And very much like the Foldscope community, now it's a robust community of roughly around 500 instruments around the world, all built by people, engaged. The data is starting to flow in. All of that data goes in a public repository that anybody can analyze. And today morning, I was looking at Twitter to find just pictures. This is the type of data sets that come out of the community itself. There's lots of sets of applications people have built on top of it for many of the algal blooms, many of the aquaculture applications. And one of the things that I'm really excited about is the fact that people get to build on top of the platform. So for often enough, we would share the platforms, but not dictate what people should do with them. So I'm going to say one more story about microscopy, and then I would really want to take you to the world that I had said that the microbial world is bizarre, which is I want to talk a little bit about malaria, because I had mentioned this to you from a health perspective. Microscopes are playful. I hope you've seen that. Microscopes allow us to see what's happening right under our feet in our ecology, but microscopes are also essential for our health and our lives. I was here before coming, as often people do. I typed in ChatGPT, what are the 5 most important tools for science? Microscope came as number 2 tool for science. I actually don't agree with it because it says mathematics as number 5. As an applied mathematician in the past, I think mathematics is pretty high up there too. But literally 2/3 of all discoveries in life sciences actually come from microscopy. And one of the challenges that we've been thinking about is these are all black boxes, cost $1 million or more. Very few people have access to them, and hence many of the advances in microscopy don't actually make it to people around the world. So I'm going to mention this last tool, which is called Octopi, which is now a completely autonomous solution for doing disease diagnostics. And for the first time, I was feeling brave, so I decided to do a live demo. We've actually never shown this demo before. We're going to try to diagnose whether I have malaria on the stage. And we'll see how that goes. I was in Liberia some time before, so. And of course, vivax, which is a species of malaria, lives in people for 30, 40 years. So you can get symptoms long times after because it can hide in the liver. One of the things that's been powerful is, again, using the same framework of open hardware and building applications on top of it. So that instrument, again, is completely open source. People can build it, and we've been building large number of applications on top of it. But let me just take you to a village that has malaria so you at least feel what does it mean to live with malaria? Why do we care? I think I talked about this. This is the reality of malaria diagnostics. We need to do roughly around 3 billion tests per year. And the current sets of standards, we can do maybe roughly of the order of 200 to 300 million tests. And the reason for this is how cumbersome it is. In 1904, when von Giemsa described the malaria test, this is still the gold standard of malaria diagnostics. This is one of our field sites in Kalahandi. This is in Orissa in India. And what you're seeing is Prem and Durga working 8 to 10 hours a day on a microscope diagnosing this disease. And no matter how hard they work, they can spend half an hour to 45 minutes diagnosing the disease itself, and then they will report it. And human errors is one of the biggest reasons that most of the specificity and sensitivity of this test can be as low to 40 to 50%. At that point, you could toss a coin. And one of the things that we've been thinking about is with the rise of the malaria number of cases itself, the malaria disease has now found a way to essentially circumnavigate the diagnostic test itself. So there is a strain of malaria that's circulating now that does not have the gene that we use for diagnosing malaria itself. So that by itself is a huge problem. And living in San Francisco, to me, it was always this matter of shame where I could see a self-driving car. I could take a Waymo on my phone to go to do my grocery. And for the last 150 years, we haven't been able to tackle this disease. And that's a shame that I want to share with all of you. Because frankly, it is important for all of us to be thinking about things and technologies that can save lives to actually reach people. And one of the things for us was, let's do this as a framework in a modular manner. And we started realizing some really interesting things. So first of all, why can I do this demo today? It's only because of GPUs. So many of you have actually unknowingly contributed to this solution. Without a gaming laptop, which I have right here, we cannot do this. And at this moment, we can essentially image between 20 to 30 million cells in a period of 5 minutes and do diagnosis at an accuracy of 5 parasites per microliter, which is one of the gold standards in microscopy. So the compute hardware had to be there. We had to build tools in a modular manner. It took a long while since 2015 when we started working on this to a point where now we are starting to ship this as a solution. And one of the things that I'm excited about is I'm just going to do a live demo and see how that goes. As is often, I was thinking of drawing blood, but then I realized some of you might not like it. So I'm not going to poke myself, but what I've done here is if we go back to the laptop again for a second. This is live at this point. This is a smear, and I wanted to show you a positive smear. So this happens to be a patient from Uganda. I've actually loaded just a simple glass slide, and later on you can come back and see this. That's loaded in here at this point. And just before running the demo, I had run it in a second, it identified in all of these fields of view, it's identified parasites live. So I'm just now going to try to do this live. I go to new patient. Imagine you walked into the clinic, and I'm going to hit that. The instrument at this point, as you will see, is starting to search and focus. And once the focus finishes, all of this is happening hands-free. I'm not controlling the machine at this point. And one of the important aspects of this is the reason we could do this is actually a trick from astronomy. In astronomy, you actually don't just look at the stars, you actually look at the color of those stars. And we made this discovery some time ago. So at this point, it's starting to scan the fields of view. And in real time, every second I speak, it's looking at between 10,000 or so cells and identifying parasites in them live. And this is literally, I mean, it gives me goosebumps sometimes looking at this, because now finally we can be in a stage that in a rural clinic anywhere in the world, we can essentially do real-time diagnosis. So if we can switch back to the other slide, and this is going to continue for a while. Unfortunately, this patient is actually dead. The parasitemia is so high. This is falciparum. This is one of the deadliest diseases in the context of malaria. And at that parasite level, you just have absolutely no survival. And one of the things that started to happen for us in the context of malaria is the point that I mentioned about spectroscopy. We discovered that we can label DNA and RNA with the same molecule, but the configuration and how the molecule of DNA and RNA is slightly different. This optical probe fits in that slightly differently. And that gives us a spectral shift of color. And you can actually see the blue is DNA and the green is RNA. And that becomes a signature of a parasite that we can use to diagnose and identify parasites. So I'm going to skip much of this because we just did this live. For the last couple of years, we've been starting to share this. So it's a large community of around 25 hospitals across the world. We've been building these sets of tools, and something really surprising happened. Again, the same lesson that I had talked about in Foldscope played out. Because we built an open platform, we invited others to engage. And something interesting happened when I was in Rwanda. They said, you know, malaria is important, but we also have a massive amount of head and neck cancer. We have all these patient data set. Could you do that? Suddenly, we were in South Africa, and the biggest thing that shot out is MDR-TB. We were in Nepal, and one of the big things that people also cared about is, could you do sickle cell anemia? And that started a chain reaction for us to think about, could we build one single instrument that could actually identify hundreds of infectious diseases? So at this point, already the instrument that I showed you diagnoses malaria. We've been able to build preliminary data for TB. We have a clinical study that's being published with the group in Nepal, where majority of that work on the ML was done in Nepal itself. For sickle cell anemia, we have a recent paper on sepsis, and one of the things that it's starting to feel like is, could you actually build an app store for diagnostics? And the reason this is possible is, again, the openness to share and share the value amongst people that would care about tackling these sets of diseases. The entire infrastructure is completely open and modular. So just like you build your computer, you could go tomorrow and build some of the best grade microscopes in the world, all online, completely online software, a massive support community. And that led to this instrument gave birth to an entire host of research instruments that are now catalytic in many of the sets of communities that have never had the chance to essentially study the sets of diseases that they're inflicted with. And the case in point for that is Liberia. I was in Liberia a couple years ago, and one of the things that struck me was how little of the infrastructure that we had thought that we had put together for Ebola remained. Primarily because it was all closed sets of solutions. Most people didn't have access to them. There were no sets of reagents. And most of the solutions were extremely fragile, so they didn't last long. And ironically, the case study that we've been working on is we've been working on Ebola patients that survived without a vaccine. There is something very special in their immune system. But every single sample from that cohort gets shipped to the US, gets analyzed here, and much of the data doesn't make it to the Liberian scientists itself. And so one of the programs was to actually build and install the scientific instruments that can be built. So this is one of the first codex platforms now in Liberia, and one of the first instruments of this kind in a country like that. And this has been on and on in terms of thinking about many sets of places that have tremendous talent, tremendous access to the kinds of diseases that we need to all care about, but absolutely no access to tools for discovery. And that's really the only message I want to communicate, is that tools of discovery are essential if we're going to progress science in an equitable manner. We run training programs around the world for, not just putting a website together, but to really hold hands, just like you would do for your community, to really bring people in these sets of communities. And there is a very large class of instruments that we're now starting to release, which start to look like computer farms, but they are microscope farms that can mine through massive amount of data sets for discovering new drugs, to be able to looking at infectious diseases, and to be building a kind of a platform that you could just talk to in a completely autonomous manner. Okay, so that was my comment on malaria. In the last 10 minutes I have, I want to go back and prove to you that the microscopic world is truly bizarre. I've scared you a little bit, but I want you to be also realize that it's the most playful world that I know of. So the last sets of pictures and videos you will see will pass by very quickly, and I'll tell you a really surprising thing that I found. I told you I was 15 days ago in the Pacific Ocean, and I want to share what I found from the depths of the ocean that I'm just so excited about. But before that, let me just tell you how bizarre the microscopic world is. So in that photograph right there, I mean, of course, there are hundreds of thousands of these little creatures out there. Right behind the Facebook or the old Facebook office, there used to be a swamp. I have a tendency to take all the students that come to my lab to this swamp. And one day in that swamp, I picked up something quite strange. And I'm going to show you what that is. This was literally with a $2 instrument in the middle of a swamp. This is what we saw. The data set that you're seeing is what we collected with the Foldscope itself. The organism is called Lacrimaria. And if you want to, there's a little bit of a music in this. But this is a single cell. What you're watching is a living organism in real time going about its business. It's not a worm. It's not an animal. It's a single cell. Now that single cell has this very strange hand or neck, which we call it, and you see what it's about to do right there. That's a strike. This guy is a predator. It's a mean predator. If you were sitting right here, you would have something large come about and gobble you in real time, and then it goes about its business. To kind of scare you a little more, we brought this to the lab. We were the first lab to be able to culture this animal or cell in large numbers, and we started observing, and we saw something really, really bizarre, which is the fact, first of all, it's not cannibalistic. It knows what it eats, so it doesn't eat its brothers and sisters. But look at this. What you're watching here is the cell is only 40 micron in size. That's half the human hair width. But it has a capacity to extend this neck to 1 millimeter or 2, 100 times its size. So I have to say here, I often say, who has seen the movie Incredibles and knows about the stretch mom? In this audience, I have to say, who was involved in making that movie? So it's literally that, but for real. And I don't know if you guys knew about it, but one of the things when we discovered this, we were shocked because that doesn't hold the laws of physics. Matter cannot appear and disappear in real time. And so we were really puzzled, and we started thinking about this. First of all, they do this little dance. Where does this come from? This doesn't have a brain. There is no nervous system here. It's a single cell that's making these sets of behaviors. And to just really scare you, this is what it looks like up close. And if you were microscopic, this is what would happen to you. That's the strike. And you start seeing these little wiggly lines or hair-like things. These are called cilia. This is what's actuating the system. That's effectively the brain of the system. and in real time, it has the capacity to morph. There are two lessons that we learned by just going to a swamp with a $2 microscope that now have transformed our understanding of cell biology. This is the first time now we can understand how an algorithm is implemented in this very simple system. The algorithm is actually, this is a chaos-generating machine. And what I mean by that is, on the left, you see a computational model. These cilia turn on and off, and this is a very famous theorem in physics called the non-conservative forces or follower forces. And what's happening is at the tip, and some of you who have thought about rockets, there is an association of this with rocket physics as well. What's happening is at the tip, the force that gets applied to this filament is actually always tangential to the filament. But because the state of the filament is dynamic, that force orientation is dynamic. So the system knows its state at all times, and we can model this, for example. And when you model this in a simple kind of a context of just a beam and activity at the tip, they form periodic oscillator. No intelligence, just the red tip is turning on and off, and you form these beautiful oscillators. Some of these oscillators are very strange because they have 10 cycle, they have 11 cycle, and try predicting where the neck is going to go next, and it's actually quite hard, but it is quite periodic. But in majority of the cases, this is actually a chaotic system, and chaos leads to randomness, and this thing is doing a random search in space. So the search algorithm is embedded in this very simple geometrical form. And to just give you a sense of what the aperiodic side looks like, when we do a scan of stiffness of this object and activity, you can essentially find this beautiful landscape that the animal or the cell is able to search its space in, by being a chaotic oscillator. Now, this is the first example of embedding of an algorithm that was actually discovered in a single cell. And if you want to do this experiment, go home tonight or whenever you go home, hold a hose a little bit far away and turn it on fully. I promise you, you will get wet, but it's the same physics of garden hose instability that actually applies here. Okay, so that was one surprise, but there is a hidden surprise about extension. I told you that this thing can extend a millimeter or two. How the hell does it do that? This is a real-time video of the cell extending these necks long time ago. We started torturing the cell. We can hold the cell, and I can't say it doesn't hurt because I don't know. But we're going to hold it with 2 pipettes, very difficult experiment to do, and we will just pull. And we keep pulling and pulling and pulling, and we can extend out a neck that's 3 millimeters long, which is astonishing to think about. Where does all this membrane come from? And we started looking at the architecture, maybe just 2 more minutes. Yeah. And we just realized that there's a beautiful architecture hidden inside this organism that enables origami. So this is the first example of cellular origami, and I'm just going to show you that origami. This is the architecture. This is the hidden beams inside the surface of that cell. And it actually is a new kind of origami. We call it lacrigami, which is spiral pleats on a cylinder. Now these are membranes that are literally tens of nanometers supported by elastic beams that are 40 nanometer. Now this is a macroscopic version of it. And what's very beautiful about this mechanism is that the control for deployment and redeployment of the system is embedded in a singularity that's associated with D-cones as they travel in this origami. So many of you know James Webb Telescope. We were all so scared whether it's going to open or not. $1 billion is going to go down the drain. This organism opens and closes this origami 10,000 times in every 15 minutes. So just from a robustness point of view, it's just a beautiful mechanism that we would have never discovered if we hadn't gone to the swamp. Okay, I think I'm out of time. I'm just going to share one bizarre. I wish I could go all the way to the back, but I can't. You know, this also inspired us to build a mechanical intelligence in mechanical objects now. So we have a version of this paper that talks about how to build literally mechanical intelligence in objects of springs. And I unfortunately just ignore some of these slides because I want to get to the very end. I do want to show you something about the expedition. So, and again, all of these sets of principles all arose from just watching these sets of organisms do what they do. This is another organism that we found using a Foldscope. It's one of the fastest contractile cell that we have ever discovered. 5 millisecond, 15 G forces of contraction in a single cell. And one of the things that's valuable is that this organism actually uses this to talk to other cells. So this is a high-speed video, and what you're watching is these cells are literally talking to each other at 0.5 meters per second. Just like I'm sending a pressure wave to you and you're listening, they are sending a pressure pulse to talk to each other. Again, I'm super excited about this discovery, all because we were looking in swamps and places. Okay, I think I have to skip all of this. There is a lot of beautiful things to look. Another discovery we made with the Foldscope is how organisms build single crystals. So many of you know about how snowflakes are made. This is akin to a snowflake, but built inside the body out of single crystals. And one of the things that is exciting about this is the mechanisms that it does that. Actually, I'm wondering is there a way to get to the last slide? Or I could stop here and then take sets of, at least because there's just 5 minutes. Actually, let me stop here. I'll stop here with this video to just give you a sense that, one of the challenges that's associated with some of this work that I'm describing is you have to be embedded in an environment and you have to be exploring. But the planet is a big place, and unless we can give the access for everybody a chance to explore, we will never be able to really discover and find in an equitable manner the sets of solutions that all of us actually need. It's not an optional thing that, oh, this is a nice to do. It is really a necessity for society as a whole to operate and work in a functional manner. Okay, I'll stop here, and we have 5 minutes for questions. And then I'm around all day, so I'm happy to talk.
Let's do all the questions in a row, okay? And save for just one big answer.
Yeah. And I'll answer them exponentially fast.
Exactly.
So,
please.
Yes, hello. My name's Jeffrey Weekly. I'm from UC Santa Cruz. I understand that you're doing inferencing on the local machine. Where are you doing the training?
Yeah, so the training also we do locally on the machines themselves. And one of the big things that we've been building is for malaria, there doesn't exist a data set of patients. So we've been recruiting patients around the world and setting up these sets of machines. And one of the key ideas here is that the data quality has to be the best. And that's the whole purpose of installing the first 25 machines in institutes across the world. Because I can culture malaria in the lab, it doesn't look the same when it comes from patients.
Great.
So, really inspiring work. Thank you for the talk. The connection to GPU advancements and the App Store of Diagnostics are very heartening. A quote that jumped out to my mind.
So please keep playing video games. Yes.
The quote that jumped out to my mind, though, is Quest Diagnostics hates this one simple trick. So I was wondering if you've run into any challenges of that type.
Yeah, I don't really care. I think let the world do what they want to do. And I think that's the shortest answer. Yes.
Yeah, thank you for the talk. I was wondering how many or how these organisms are the influence or are created by the impact of the human, and if we are leaving an impact for a long time at this microscopic level.
Yeah. We are losing species faster than we can find them. As we speak, when you annihilate an ecosystem, literally hundreds of thousands of species are lost. And the thing that I wanted to show you guys is in one of the expeditions in the California currents, I met a single cell, one single cell, after filtering 100 million liters of water. I found this one cell, and the reason I'm excited about it is the fact that that cell has never been seen. It's only been seen once in 1898, and there is one drawing of that cell, and since then nobody's been able to find it. And it required that much amount of work for me to be out there for 30 days filtering to meet this one cell. Now, maybe I have to wait another 100 years to meet another one of its kind. And so if that gets lost, I don't think we're going to know. So we're losing species far faster than what we believe. we are only counting things that we even know about. And this is really the irony of this place, that our impact on the microbial world and the other way around of how these microbes are. We were in the Arctic, and we saw the highest biomass ever observed in the ocean under the ice, which makes no sense because ice is dark and most biomass requires light. The ice is thin enough now that enough light is penetrating that there are these massive blooms. So the microbial world is changing far faster. They're going to be fine. I think we're the ones in trouble. Yes.
Thank you for the fantastic talk. I'm Octave from France. 2 days ago, I tried to get into this same ballroom, and I couldn't because there were too many people looking at two billionaires cracking jokes about the dystopian world they are building. And it seems to me that they're not solving actual problems like you are. And I feel the same kind of shame that you mentioned with the self-driving cars in San Francisco. And I was wondering if you had any ideas for leverage, for what we can do to make sure that next time you give that kind of talk, people are lining up outside, and what we can do to make sure the ecogram is as popular as Instagram and all of that. So,
yeah. First of all, thank you for the kind words. You know, I think I have to say this is that we do this because of our passion and what we all believe in. And frankly, that is what drives change in the world. This is an invitation to all of you, frankly. I mean, I didn't even talk about hundreds of collaborators that we work with. Operating and working with openness and being honest about the challenges is the only thing we will be able to get out of many of these problems. So this is an open invitation to all of you. I would love to engage. This community is just remarkable. And one of the challenges that we face is actually financing many of these projects is so damn hard. Like, I mean, you know, it took us 10 years. We built the world's largest microscopy community. That's still 2.5 million kids. I'm very proud of it. I'm very proud of every time any kid in the world gets access. But, you know, there are 2 billion kids. And so I feel a sense of burden. And one of the things that's important and valuable is to be able to get the values driving how we engage in change in the system. So, you know, if you have ways and ideas to engage, I'm all ears. You know, being able to financially support many of these things is one of the biggest challenges that we face. And, you know, I live in the Silicon Valley. I knock at the doors of many of these entities, and there is very little interest because often enough people come and say, oh, with this idea, when am I going to make $100 million? And I'm trying to say, when do you reach 100 million people? What is more important? And people can decide that for themselves. But I think this is really a real challenge. And unless we can support, and this is the tip of the iceberg. I mean, I teach this class for the last 5 years. Hundreds of ideas around the world that could truly make a difference get very little financial support to actually scale.
Thank you. Thanks a lot.
SIGGRAPH family, Manu Prakash.
Thank you.
Extraordinary.
Thank you.
Thank you very much.
Yeah. I can start unpacking and then we can... So I'll have this machine set up somewhere outside if you want to come and play. If anybody wants a malaria diagnosis, please come by. But if you have some water that you want to look at, there was a puddle look by. If you want to get yourself trained, I didn't bring that many Foldscopes, but Foldscopes are available online.
We have.
Perfect.
Thank you.